Hi everyone, and welcome to today's lecture. I believe this is our fourth online lecture for this course, and today's lecture should be a little bit shorter than the other ones. We've done a lot of work already in last lecture, which covered all of the antiderivative rules, which you'll see on the screen over on the side for most, if not all, of the lecture today. And what I wanted to cover today is material from section 6.3 in the book, which ties back together everything that we did in chapter 5 with the new rules and techniques for finding antiderivatives that we covered in last time's lecture. So today's lecture is titled Evaluating Definite Integrals Using the FTC. Remember, the FTC stands for the Fundamental Theorem of Calculus. And I'm going to write out once again for you guys the Fundamental Theorem of Calculus, because it is really just that important. Alright, so the Fundamental Theorem of Calculus states that if the function, this is a derivative function, f prime of x, is continuous, instead of saying from, I'll say for x values that are between a and b, then it turns out that the definite integral from a to b of f prime of x dx is going to be exactly equal to f of b minus f of a. And we had stated before that the interpretation of this is to say that the definite integral of the derivative we'd stated that that is equal to the total change of the function. Okay, so this is super important. This is the fundamental theorem of calculus. This is the way that we've learned it before. But with the tools that we've developed with last week's lecture, there's actually a separate, different way that we can rephrase the fundamental theorem of calculus, which will allow us to evaluate definite integrals very, very easily. And here it is. So I'm going to call this FTC. These are both the same statement. I'll call this version B, or version 2, which states the following. If capital F of x is an antiderivative of lowercase f of x, and again, this is for a less than or equal to x less than or equal to b, then the integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a. And another way to phrase this, using the same idea here, is that the definite integral of the function is exactly equal to the total change of the antiderivative And this is the version that we're going to be using to evaluate all these definite integrals. Because very simply, this gives us a technique, a method, that we can use to evaluate definite integrals in a very straightforward and immediate fashion. So let's write this out. To evaluate the integral from a to b, definite integral, of f of x dx, first find the integral, indefinite integral this time, of f of x dx. Give this a name, say capital F of x, and then compute f of b minus f of a. All right, this is all it takes. This is the entire technique. This is going to allow us to calculate definite integrals in a pretty fast and straightforward fashion. And this is also the reason why I'm leaving up all of these antiderivative rules over here on the side of the board, because we're going to be using these quite a bit. Now remember, as we work through these problems, that definite integrals correspond to area underneath a curve. Or more specifically, they correspond to the area beneath the curve of the function that you're integrating, or between the curve of the function that you're integrating, and the x-axis. So remember what we said a while ago about being able to count negative area? You have to be careful about that here. We'll get to all of that later. First off, let's do some examples. Okay, let me select what I want to select down here. Let me get rid of this. And let's get started. So the first thing let's do is let's find the integral from negative 2 to 2 of x squared dx. All right, now to give you guys a quick recall about what this function looks like. If this is the x-axis, this is the y-axis. And down here is going to be 0. This is 1. This is 2. This is 3. And this is 4. This is going to be negative 1. This is going to be negative 2. This is going to be 1. This is going to be 2. Again, apologies, I'm not the best drawer of all time, especially not on a tablet like I'm working right now. But nevertheless, the function that we're looking at looks something like this. And the question of evaluating this definite integral actually comes back to computing this area here in red. So this is this area. And I do include both sides here. So all of the area that you see calculated in red is what is being calculated by this definite integral. Okay, so let me make sure I'm in the right color here. Step 1. So the first step is just going to be to find the antiderivative of x squared dx. And this, by power rule, by the rule number 1 that I've written over here on the side, is going to be equal to 1/3 of x cubed. And this plus c this time, and every time we're doing definite integrals, this plus c is not actually that important. So it turns out that at the very next step, in step 2, no matter what this plus c is, it's going to go away because it's going to cancel out with itself. So let's see how that works out. Step 2. So let's call this function capital F of x. Step 2 says just find capital F of 2 minus capital F of negative 2. And if you do this, you're going to see you're going to get 1/3 of 2 cubed plus c minus 1/3, mind the parentheses here, these matter, of negative 2 cubed plus c. And the first thing that you'll see is that these c's cancel out. So they go away right away. All right, let's see what we're left with. We get 1/3 times 8 minus 1/3 times negative 8. This becomes equal to 1/3 times 8 plus 1/3 times 8. And this is going to be equal to, I believe, 16/3. And this is units squared. So the reason why I say units squared is that however long we decided to make in this graph 1 unit here, is going to be the exact unit of distance that we're using here. So if each increment of 1 on this graph were actually drawn out to be 1 inch, then the area on the graph would be 16/3 square inches. Okay. So hopefully you guys can see how this is a pretty easy method for calculating these definite integrals. Because as long as we're able to find the indefinite integrals using all the rules that I've put up here for antiderivatives, then all you do is you plug in the first value, you subtract what you get when you plug in the second value, and you get the area, you get the exactly what your definite integral is equal to. Okay. I accidentally deleted a line I didn't want to delete here, so let's draw that back. Okay, so let's do a couple more examples of how to compute some of these definite integrals. Let me change the size of my pen a bit, make it a bit fatter. All right, so the next example, I'm not going to do a drawing of the area that we're calculating each time for all of these, especially because some of these shapes will get relatively messy. But for now, let's stick with, let's say, integral from 0 to 4 of 2x plus e to the x dx. Okay, so here I'm going to show you guys, this is an example, but this is also going to be notation. Because there's a shorthand, as you guys have probably realized by now in all of your time taking math courses. Mathematicians like me, we like to use shorthand. I know it's sometimes hard to keep all this in your mind or in your head to know exactly what all the shorthand means, but please do understand that the shorthand actually saves us a lot of time, a lot of energy. It's like a language that we use to communicate efficiently among ourselves. So there is a point to doing all of this. Regardless, the first thing that we do, step 1, is to calculate the indefinite integral of 2x plus e to the x. So you'll see here, what I'm going to find here is just the indefinite integral of 2x plus e to the x dx. I'm going to write that out here. And you'll see that first off, using the power rule, we see that the integral of 2x is going to be equal to x squared. And using the exponential rule, we see that the integral of e to the x is just e to the x. And remember that the step number 2 is to plug in 4 into this function, and then subtract what you get when you plug in 0 into this function. And here's where the shorthand comes into play. We'd like to put a vertical bar here. And at the bottom of the vertical bar, we put a 0, and at the top, we put a 4. All right, what does that mean when I write this vertical bar here? That means that we are taking 4 squared plus e to the 4 minus, mind the parentheses, these parentheses are important. Here we have 0 squared plus e to the 0. Now if you plug this in, 4 squared is equal to 16, plus e to the 4, there's no way to simplify e to the 4, it's just some number. 0 squared is 0, e to the 0 is 1, and so we see that our definite integral is equal to 15 plus e to the 4. And that's our final answer, and remember that this would correspond to the area between the curve 2x plus e to the x and the x-axis from x equals 0 to x equals 4. Okay, for now, I'll make this guy smaller as we work through a second example, just because I'm not going to rewrite the indications of all the notation every time, so you can at least see what I'm referring to. Let's do another example. Let's take the integral from 1 to 3 of 2x squared plus 4x minus 1 dx. Okay. So we're going to have to use the power rule a bunch of times here. You'll see that the integral of 2x squared is going to become 2 over 3 x to the third power. The integral of 4x is going to become 2x squared. And the integral of negative 1 is going to become negative x. Again, in all of these cases, you would have, if you were doing an indefinite integral, a plus c. But whenever you do definite integrals, your plus c's cancel out and you don't have to worry about them. And then I'm going to do this vertical bar again. Put a 1 at the bottom, put a 3 at the top, and that's indicating that I'm plugging in 3 and subtracting what I get when I plug in 1. So let's try this out. So first off, we plug in 3 to see that we get 2/3 of 3 cubed plus 2 times 3 squared minus 3. And then we subtract what we get when we plug in 1. Mind these parentheses are important. Whoops, not a 3 there, this should be a 2. 2/3 of 1 cubed plus 2 times 1 squared minus 1. All right, so one of these 3's is going to cancel. I don't have too much space here, so let's try to do this efficiently. This 3 down here is going to cancel out with one of these 3's, so that this is going to be a 3 squared. This is just going to be 2 minus 1. Let's work all of this out. we're going to be left with 2 times 3 squared plus 2 times 3 squared. So 2 times 3 squared is 2 times 9, which is 18, plus 18 minus 3, minus 2/3, minus 2 plus 1. And if you add all of this together, 18 plus 18 gives us 36, minus 3 is 33, minus 2 is 31, plus 1 is 32, and this is 32 minus 2/3. So if you want, you can rewrite this as 31 1/3. But I prefer to write it like this. This is going to be the final answer for this definite integral. Okay, so this is actually about it for what I wanted to cover today. But there's just one more thing. I just wanted to tie things back together with one section of a previous lecture on definite integrals. And this section involved, I gave it what I think is the appropriate title, called funky shapes. So let's look at some funky shapes. And remember that funky shapes correspond to finding the area between two curves. Okay, so I don't want to do too much here. I'm just going to do one example of a funky shape whose area we can find by using definite integrals, by using the technique for finding the area between two curves. And it's going to be the following shape. So I'm going to graph it with a normal graph. Like this. Like this. And this graph is just going to go from 0 to 1. And the two curves that I'm going to be looking at are going to be the curve, or rather the line, y equals x, and then the parabola down here, which is y equals x squared. And so the question becomes, how do we calculate what this area in red is equal to? So this is my question. What is this area? Okay, so recall that the way that you calculate the area between two curves is that you first identify which curve is above the other. In this case, y equals x is the top curve. Meanwhile, the curve that is below is y equals x squared. And then you find the following definite integral. You're going to take the integral of the top function and subtract from it the bot function. And we're doing this definite integral from 0 to 1 because 0 to 1 is the interval we're looking at here. Okay, so let's plug everything in. This is looking at the definite integral from 0 to 1 of x minus x squared dx. All right, so the first thing that we do is we integrate this, just indefinite integration. The integral of x by power rule is going to be x squared with a 1/2 in front because the new power is 2. And the integral of x squared is going to be x cubed with a 1/3 in front because the new power is 3. And we're evaluating this from 0 to 1. So when you plug in 1, you'll see that this is 1/2 minus 1/3. And then you subtract what you get when you plug in 0, but you'll see that when you plug in 0, this is just 0 minus 0. And so the final answer that we get here is just going to be 1/2 minus 1/3, which is equal to 1/6. So what have we learned from this example, from this very simple but I think visually interesting example, is that this is a weird shape that we've cut here, right? It's like a little slice of a parabola that we've taken, like a sort of diagonal slice of one. And we've asked ourselves, what is this area equal to? And I really want to emphasize that without the tools of calculus, if I asked you guys, what is this area equal to, you would really have no idea where to begin. Because we don't have any geometry formulas that will allow us to actually calculate the area of anything that looks like this. All of our geometry formulas are for polygons, basically. So things that only have straight edges, right? Nothing curved like this. That, or maybe we have a formula for circles, but this isn't even a circle, right? So without calculus, we'd be lost. Even though this isn't even the funkiest shape I could come up with, you still wouldn't know how to find the area of this shape. But now that we have these tools of calculus, this was actually very straightforward, basically just 2 lines of work, and we found that the area of this shape is 1/6. Okay, that's pretty much all I wanted to cover for you guys today. This is really just trying to tie the room together here, trying to tie together all these antiderivative rules and all those ideas that we took from last lecture, along with all of the stuff from chapter 5, which we covered last week, and seeing how we can combine all of these to pretty quickly and efficiently calculate the areas of shapes and calculate the values of definite integrals by using these antiderivatives and the fundamental theorem of calculus. All right, as usual, if you have any questions, any concerns, or would like my help with anything, just let me know. Shoot me an email. Even leave a comment if you want to. Otherwise, I hope everyone is staying safe and healthy at home, and I'll catch you guys again next week. Bye-bye.